everyone, and welcome back to our series on exploring neutrinos at the college level. Last time we drew comparisons between the rather familiar world of Newton and the rather unfamiliar world of tiny particles to make sense of this equation, the evolution of one neutrino mass state in time. In this episode, we'll finally reveal what this means for neutrino flavors. Because at the end of the day, we're not trying to weigh our ice cream, we're trying to take a bite. Do you recall the concept of a dot product between two vectors? For example, if I had two vectors, unit vectors, A and B, I could ask the following question. How much of vector B falls in the direction of vector A? To do this, I would multiply the x components together, add them to the y components multiplied together, and then add that to the z components multiplied together. My answer would be some number between -1 and 1, with -1 happening if vector B was completely opposite vector A, and 1 happening if vector B was completely in line with vector A. For simple vectors, this dot product serves as a means of figuring out how much two vectors look alike. And this is exactly the process that we want when we're looking at our neutrino states. We could then ask ourselves how much a neutrino flavor at time t looks like the originally prepared flavor. And luckily, this dot product-like operation already exists. Here is the original flavor state for an electron neutrino, and here is the state at some time t. Just like with our unit vectors A and B, we can multiply similar components together and then add them up. The only difference is that we'll take the squared absolute value here. This looks pretty similar to what we just did, right? Here's the normal A dot B expression with three position coordinates, x, y, and z. And here's the quantum mechanics version with three states acting like x, y, and z coordinates. This quantum mechanics quantity is the same thing as asking what is the probability that the neutrino flavor we have at time t is the same as the one we started with. Think about that. What would we want this probability to equal? If we were in our everyday world with ice cream, we'd expect, hands down, that our ice cream flavor would not change after a few minutes or so. That would be insane. So we'd expect the probability to be 1 here. Or in other words, we'd have a 100% chance of keeping the same neutrino flavor at time t as we had at time t equals 0. But this isn't ice cream. This is the world of tiny particles. Take a look at this expression that we're hoping equals 1. Do you think it does? It may not be a surprise to you that it doesn't, for how messy it looks. And not only does it not equal 1, but it doesn't equal a constant in time either. This expression is a periodic, changing function in time, meaning that our initial electron neutrino has a probability of switching flavors over time and even oscillating between them. The ice cream business just got a lot more complicated. This phenomenon, called Neutrino Oscillations, this is our reality. And if you put your fingernail up to the sun, trying to get in the way of the many, many neutrinos that it produces, every second that passes by, enough of them will pass through your fingernail for every person on the planet to have a handful. And they're all in the midst of shape-shifting, of changing flavors, of oscillating, while zipping through space at nearly the speed of light. Can you believe this, though? Neutrinos don't keep their original identity. They don't keep their original flavor. And our intuition for the everyday, how reality looks, appears to fail us here. But this is why these particles astound us. This is why they're worth studying. This is why we invest tons of money into collaborations to hunt them down. This is why we're determined to seek out more answers. Because this is only the beginning of their story. As always, thank you so much for watching. Take care for now, and never stop learning.